Once you know about filling the electrons, now we can go on to talk about bonding, because you need to understand the concept of valence electrons before we can go into bonding valence and core electrons. So in this case, we'll learn about bonding between metals and nonmetals, which is ionic, and then between nonmetals, which is covalent. So this is really quite a huge chapter, and it's a continuation of chapter 2. If you remember, we kind of introduced this concept way before. The first thing we start with is what we call the Lewis dot symbol. And a Lewis dot symbol is whereby we indicate how many valence electrons are in any atom. And then they are shown as dots. Okay, and so the dots are drawn around the atom. Now, when you draw the dots around the atom, they're drawn in very specific location: top, bottom, left, and right. Okay, so which means not in the corners. Remember, the corners are already taken up by the charge, the subscript, and then the mass number and the atomic number. So don't take the corners, write all the electrons only on the left, right, top, or bottom. So the Lewis dot structures show only the valence electrons in any of the elements. Now, the valence electrons are given by the group number. So in group number 1, you have 1 valence electrons. In group number 2, there are 2, and then 3, 4, 5, 6, 7, 8. Okay, so those are the valence electrons that are present. So which means at any given time, there are only 8 electrons, okay, in the outermost shell. Bonding is a property of valence electrons, not so much of core electrons. The only time that we use core electrons in bonding is when we talk about transition metals, which we are not talking about right now. We are sticking with the main group elements, which is the S block and the P block. So you can draw the Lewis dot symbols as dots. And sometimes in my case, I draw crosses also. Okay, so dot or crosses are fine. And I'll show that in the class when we go through this. As you can draw either of them. Okay, crosses or dots, any one of them is fine. If you draw a dot, make sure that it looks like a dot. Okay, and not just a point anywhere. So be symmetrical when you're drawing these electrons out. So you can start from the left or right or top, bottom, it doesn't really matter, but try to be as symmetrical as possible. So for example, when you get to the 2 electrons, you draw them in opposite sides, 3 on 3 directions, 4 is 1 on each side, and then you start pairing electrons. Remember how it was when we were filling out the box configurations, is you fill everything singly first and then you pair. It's the same philosophy here also. Okay, so fill the electrons singly first and then you start pairing them up. Okay, and again, make sure you don't take the corners, you only take the sides. So then our next question is, why bonding? Okay, why should anything bond at all? And if it is bonding, then what are the different kinds of bonding? So first of all, bonding occurs to make elements more stable. All right, if elements were stable enough, they will not bond. So for example, noble gases are stable enough. They do not need to bond with anything. They're called noble gases because they refuse to bond with anything. And they're also inert gases, non-reactive. So why is this occurring? This occurs because their electronic configuration is quite different. How is it different? It is their valence shell is full. So each of the noble gases will end in S2P6, which means that they have 8 electrons in their outermost shell, which is the valence shell. So if the valence shell is full, that means any element is going to be stable. So then all the elements try to reach to that noble gas configuration, which is S2P6, all right? And that magic number is 8 electrons in the valence shell. This is called the octet rule. And in the octet rule, all elements will try to reach that 8 electrons in the valence shell. How they reach there, that's a whole different thing. And this is where the types of bonding comes in. So there are 2 kinds of bonding, ionic and covalent. In case of ionic bonding, there is transfer of electrons, which means that one gives, one takes. In case of covalent, it's the sharing of electrons. There is no give and take, so there is sharing. Ionic bonding is between metals and non-metals. Remember, metals are the left-hand side of the periodic table and non-metals are the right-hand side. And in covalent, it's between non-metals only, which means only the right-hand side of the periodic table is involved in covalent bonding. In case of ionic bonding, you will find cations and anions. Cations coming from metals that have given electrons away, and anions coming from non-metals that have actually accepted electrons. In case of covalent bonding, you will not find any ions because There has not been any give or take of electrons, it's only sharing of electrons. So there are no ions here. And one of the properties of ionic compounds is that they have really high melting points, whereas in covalent compounds they have low melting points. So those are some of the properties of ionic and covalent bonds. Let's look at ionic bonding first. Ionic bonding is made from transfer of electrons, as we just said. Metals lose electrons and become cations. Metals, remember, have low ionization energy, so they lose electrons quite easily. Non-metals, on the other hand, will gain electrons and become anions. And non-metals have high electron affinity, okay, which means that they give a large amount of energy out, which means it leads to more stability, so they gain electrons. One of the things you have to think about also, why metals will lose electrons in ionic bonding has to do with reaching that magic number 8, okay, which is a stable octet. If you look at sodium, which has only one electron in the outermost shell, in the valence shell, it will take a lot more energy for it to gain 7 electrons to become the stable octet rather than lose just 1 electron and become a stable octet, okay, because then the next shell over will be all completely full, okay, and so that's why metals would prefer to lose electrons, because it's easier for them to lose the less number of electrons rather than gain many number of electrons. The same thing goes for non-metals. They will prefer to gain electrons because it takes only 2 or 3 to gain electrons and then become the stable octet, rather than trying to lose 7 electrons or 6 electrons to become the stable octet. So that's another reason why you can think about metals and non-metals doing what they do. So what's the deal here then? Metals will give electrons to non-metals, because metals are the one losing electrons and non-metals are the one who need those electrons, and so that's a nice kind of partnership going on. So what we do in case of ionic bonding is we write the Lewis dot structure of both the starting materials that we have, of whatever it is that we need to bond, and then we'll show the transfer of electrons, okay? And so for example here we have calcium and oxygen. Calcium has 2 electrons in the valence shell and oxygen has 6. So oxygen needs 2 electrons, which calcium will give to oxygen. So now calcium becomes Ca2 plus and oxygen becomes O8 and then the 2 minus, okay, over here. So when you draw the Lewis structure for ionic bonding, you have to write Ca2 plus, and then in square brackets you have to write the oxygen with the full octet and then the 2 minus, which is how many electrons it has gained. There is no plus sign when you're writing the Lewis structure for ionic bonding, okay, but that is how simple ionic bonding is, and you've done this a lot before in chapter 2 when we were going through nomenclature. So here is one more again, sodium and chlorine. Sodium needs to give 1 electron and becomes Na plus. Cl needs to gain 1 electron, okay, and becomes the chloride ion. So the way it works is that sodium will give that 1 electron to chlorine, and then here is the Lewis structure for sodium chloride, so Na plus. Now sodium does not have any electrons left over, and so you don't have to show any dots on sodium, but you have to show the positive charge, because that is the charge that is on sodium now because of loss of electron. And then the chlorine here with the full octet, each of these lines represents 2 electrons, okay. So here also on the left hand side, if you look, each of this line represents 2 electrons, and then of course here is the unpaired electron, which is the 7th electron. So now everything is paired up. We have 8 electrons. And because chlorine took 1 electron, you have to write the -1, okay, out here. Calcium and fluorine, calcium needs to give 2 electrons, fluorine needs only 1 electron. So because calcium needs to give 2 electrons, now you would need to have 2 of fluorines, okay, over here, in order to form a stable bond. So now we have calcium 2 plus and then the 2 fluoride ions. So you will write 2 in front of the brackets over here outside it, so you know that there are 2 fluoride ions involved with every single calcium. And then we have aluminum and oxygen. Aluminum has 3 electrons in the valence shell, needs to give 3. Oxygen needs only 2 electrons, okay, and so the best thing to do in this case is the crisscross method, if you remember. So you need 2 aluminum, which will give a total of 6 electrons, and you need 3 oxygens, which will then take those 6 electrons. the transfer should be complete. Okay, so which means that aluminum should have the octet as well as oxygen should have the octet. And so then you write 2Al3 plus for the aluminum because you needed 2 aluminum over here, and then we need 3 oxygens with 2 negative each. All right, and then again here this shows the stable octet, okay, with the 8 electrons. So the 3 actually goes again outside the bracket, not inside the bracket. Now let's look at covalent bonding. Covalent bonding is sharing of electrons. And so first of all, remember, only non-metals are involved over here, so no metals at all. So we're talking only about the right-hand side of the periodic table, except of course for hydrogen. Hydrogen is on the left side, group number 1, and that's the only non-metal on the left-hand side. So hydrogen needs 1 more electron to have a stable. We don't say octet for hydrogen, we say a duet for hydrogen because it cannot have 8 electrons, it can have only 2. So it needs 2 electrons to reach helium, which is the noble gas configuration. And so what it does, it finds another hydrogen which also has 1 electron, and then both of them share that electron. So at any point, if you count for hydrogen, so for example, if we look at just this hydrogen and count the number of electrons, it will be 2. And then if you look at this hydrogen, it should be 2. Okay, and so this is how they share electrons, and this is called equal sharing of electrons. So let's take another example, okay, where we have chlorine. In case of chlorine, we have 7 electrons in the outermost shell. So 1, 2, 3, 4, 5, 6, 7, and then the same thing over here. So again, one chlorine atom will find another chlorine atom, and it will share that unpaired electron to form the stable octet. Okay, and so this is what the structure would look like. And again, you can write all of these as lines also, just like here it's shown for hydrogen. The bonding here is shown for one pair of electrons, so you can show the same thing for chlorine also. And this would be 1 line, 1 line, 1 line, and so on and so forth. But anyhow, at any time, if you count the total number on this chlorine, it should be 8. And then if you count the number of electrons on this chlorine, it should be 8. And you have to count the shared electron also. So in case of covalent bonds, there are different kinds of bonds. Covalent bond is a little bit more complicated than ionic bonding, because ionic bonding is give and take of electrons. One gives, the other one takes, done. But in case of covalent bonding, you know, because there's sharing going on, and as we all know, whenever there is sharing going on, there are issues. Okay, and so covalent bond is a little bit more complicated than ionic bond. And so first of all, there are different kinds of covalent bonds. There's a single bond, double bond, triple bond. They all have the same philosophy, it's just that they're called different. So in case of single bond, there is only 1 pair of electron that is shared. In case of double bond, there are 2 pairs of electrons that are shared. And in case of a triple bond, there are 3 pairs of electrons that are shared by the 2 atoms. Okay, and so this is what a single bond would look like, and this is for chlorine that we just did. Okay, so there is only 1 electron pair that is being shared. In case of carbon dioxide, where you have carbon here in the middle, and carbon has 4 electrons, so that's this light green gray colored electrons. And oxygen has 6 electrons, so oxygen needs 2 more electrons, and carbon needs 4 more electrons, so it needs 2 oxygens. And so therefore now carbon has 8 electrons. So at any time, carbon is sharing 2 electrons over on the left side with oxygen, and again 2 pairs of electrons on the right hand side with oxygen. So it ends up having 2 double bonds, okay, with oxygen. Now, the double bond is considered a double bond only when it is shared between 2 atoms. Okay, otherwise it will be 2 single bonds, okay, which we will also talk about later. But in this case, this is shared between 2 atoms, and that's why it's called the double bond. And then, of course, we have the triple bond, in which there are 3 electron pairs that are being shared. So in case of nitrogen, which actually has 5 electrons, so 1, 2, 3, 4, 5. And for the right hand nitrogen, this is 1, 2, 3, 4, 5. So with 5 electrons each, they need to share 3 electrons in order to become the stable octet. So again, the left nitrogen here now has 8 electrons, and the right hand electron also has 8 electrons. 3 electron pairs are being shared in the middle, 1, 2, 3, and so they end up forming a triple bond. Again, a triple bond is only between 2 atoms, okay? And then of course we have these electrons that are left over. So while we are here, let's talk about one more thing, okay? If you can see from all of these different kind of bonding, you can see that we have electrons that are bonded, and then we have electrons that are non-bonded as well. So you can actually look at any structure. If you write the correct Lewis structure, how many electrons are involved in bonding and how many electrons are left over and are non-bonding. Both kinds of electrons have different properties, and both are important when we start doing reactions. So it's important for you to differentiate between the two, because the bonding electrons will not behave the same way as the non-bonding electrons. So for example, in case of nitrogen, there are 3 pairs of bonding electrons and 1 pair of electron left over, and 1 pair of electron left over, that's called the lone pair of electron, okay? And it's not lonely, it's just lone. In case of carbon dioxide, oxygen now has what we call 2 lone pair of electrons left over. Okay, and whereas 2 electrons are being shared here, 2 pair of electrons are being shared on either side of carbon. And then each of these oxygens will have 2 lone pair of electrons. In case of chlorine, there are 3 lone pair of electrons on each of the chlorines. So that's the difference between the bonding and the non-bonding electrons. So here is a little bit of a clue, but I would not memorize this, but it's a little bit of a clue that double bonds are formed between carbon, nitrogen, and oxygens, which means that wherever you see carbon and nitrogen and oxygen atoms, and there is a chance that it can form double bonds, okay? And then triple bonds are formed usually between carbon and nitrogen, or where carbon and nitrogen are involved. To share that many electrons, you have to have that many electrons, and you also have to need that many electrons. So for example, chlorine has many electrons, but it does not need to share 7 electrons or 6 electrons. It needs to share only 1 electron. Okay, nitrogen, carbon, and oxygens, they need to share a lot more electrons in order to become the stable octet. Okay, so one little more thing here about bond strength and bond length. For bond strength, the triple bond is the strongest one. Okay, obviously because there's more electrons being shared, it becomes the stronger bond. As far as the bond length is concerned, the single bond is the longest, which means the triple is also the shortest. And again, it is shortest because there are too many electrons being shared in there. And so that's the order of bond strength and bond length as far as double, single, and triple bonds are concerned. So bond strength, for example, for a single bond between nitrogen-nitrogen is 163 kilojoules per mole. And then by the time you get to the nitrogen triple bond, N2, it's 941 kilojoules, okay, per mole. So it shows you that, you know, a triple bond is way stronger. And then here are the bond lengths, and again remember this A with the little circle is called angstrom, which is 10 to the negative 10 meters. And so you can see from all these different bond lengths is that the triple bond is the shortest bond length of all. Okay, and so you have to remember this trend. And by the way, the example here is for nitrogen, but the same thing will follow for carbon and oxygen. You don't have to remember the numbers, you just have to remember the trend. One of the most important things that you will do from this chapter is to learn how to write Lewis structures. The Lewis structures for ionic compounds is not that hard. You just have the cation and the anion. The Lewis structures for covalent compound, as I said, are a little bit more complicated, okay, because in case of covalent compounds, you can have the diatomic molecules like the H2Cl2, N2, O2. Those are easy to write, okay, not a problem. But then molecules can get very complicated also. You can have many atoms in there, and so you need to figure out how to write the Lewis structure for these kind of molecules. So this guideline hopefully will help you a little bit, and of course we will do all sorts of practice in class that should also help you out. So first of all, draw the skeleton structure of the molecule or ion. Okay, now we have to draw ions also. You remember all the polyatomic ions from chapter 2, phosphate, sulfate, carbonate, all of those. Those are all made of non-metals, okay, and they're sharing electrons. So we have to be able to write Lewis structure of those also. So anyway, draw the skeletal structure of the molecule by placing the lowest electronegative element in the center. The lowest electronegative element is of course coming from the periodic table. You can look at the periodic table for this. Is also the one that is on the left hand side. Okay, so remember, this is not for metals and non-metals. This is only for non-metals. Okay, that's where the sharing is going on. So don't go beyond group number 4. Okay, boron is the only element in group number 3 that is involved in covalent bonding. But other than that, group number 4 is where you start with covalent bonding. All right, so if we have something on the left hand side of the periodic table, that will go in the middle, and that is also the least electronegative element. One other hint over here for drawing the skeletal structure is try and keep it as compact as possible. Okay, which means that if you have 5 atoms given to you, don't just draw them out in a line. Okay, keep them as compact as possible, as symmetrical as possible, and that will make your life a lot easier, and it will make it easier for you to understand, okay, how to write the Lewis structure. So keep it compact, keep it symmetrical. The second thing you do then is add all the total number of valence electrons for each atom, not the central one, not just the outer ones, but everything. Okay, so add all the total valence electrons. Okay, and then what you're going to do is you can subtract electrons if it is a cation. So for example, in the ammonium ion, which is +1, you will subtract an electron, and if it is an anion, then you would add the electron, because an anion obviously has more electrons. So for example, for nitrate ion, you will add 1 more electron after the total valence electrons, and for sulfate, you will add the number of electrons for sulfur and 4 oxygens, and then you will add 2 more electrons because sulfate is -2. Then the third thing you do is start drawing the structure out, okay, which means that share 1 pair of electrons between each atom. No atom is going to be disconnected, okay, everything has to be connected. So there has to be at least 1 pair of electron, okay, that is being shared. You can have more, you can have double bond, triple bond, that's true, but you will have at least a single bond. And then what you will do is you will subtract those electrons from the total number of electrons from step number 2. So if you had 4 bonds, that means you have 8 electrons, so you will subtract 8 from the total number of electrons. Then what you will do is distribute the electrons that are left over, okay, to all the atoms such that all atoms are satisfied according to the octet rule. All right, so which means that no atom should have less or more electrons. Okay, and in some cases what's going to happen is that in case where you have charges, you're going to have to see which gets the positive, which gets the negative, which means which atom has some extra electrons, which has more electrons, and so or less electrons, and we will work on that in class also. Okay, and if there is no octet that is forming, then maybe you need to form multiple bonds. Okay, all of this sounds very complicated, but really it is not. It is quite simple. Once you start drawing out the Lewis structures, you will see it's a very systematic way of drawing Lewis structures. Okay, here are some hints from you for you, and the hints here will keep your life a little sane and make sure that you're on the right track when you write the Lewis structures. So for example, hydrogen and halogens, they will always have single bonds. Why? Because halogens need only 1 electron, and hydrogen also needs to share only 1 electron. The only time halogen will not have a single bond is when halogen is in the middle. Okay, and when is halogen in the middle? It is when it is a polyatomic ion, the chlorates and the hypochlorets and all that. Okay, so other than that, if there is halogen in there, then it will be a terminal atom, which means a single bond. Oxygen and sulfur will always have 2 bonds. Okay, now I'm giving you all these hints, but then I'm also telling you exceptions. Okay, because in all these cases you will always have exceptions, and you have to be ready for those exceptions. Okay, so for example, halogens can be in the middle, okay, and they can have more than 1 bond. Similarly here for oxygen sulfur, oxygen will be in the middle, it can have 2 bonds, but sulfur can have more than 2 bonds in some cases. Okay, So you have to watch out for that. But in any case, in most cases, oxygen and sulfur will have two bonds. The two bonds can be two single bonds or it can be one double bond. Nitrogen, phosphorus, 3 bonds. Carbon, 4 bonds. Okay, and so this is how it goes. Carbon, 4 bonds. This is never, ever, ever going to change. Okay, nitrogen, 3 bonds is never going to change. All right, so long it's a neutral molecule, these things will not change. Sulfur, phosphorus, halogens, sometimes things change in there. Okay, and we'll deal with that as we get to it. So here are the steps, and you may want to keep this slide, okay, a little bit. This explains to you what we just talked about. Okay, so let's start with CH4 here. This is methane, and the first step was to draw a skeletal structure. Okay, this is the skeletal structure for CH4, keeping carbon in the middle because carbon is the least electronegative element and hydrogen is not. Again, you cannot draw everything in a line. Okay, so as I said to you, keep it symmetrical and keep it compact. All right, so this is a nice compact symmetrical structure with carbon in the middle and 4 hydrogens on the side. Then the total number of valence electrons are 8. How? 4 coming from carbon and 4 coming from hydrogen. Okay, so that's the total number of electrons. Step number 3, are there electrons left over? So what you look at now is the total number of electrons you counted, which is 8. And then you look at the bonds that you formed over here, which is 1, 2, 3, 4. Each bond has a pair of electrons. And so that is 8 electrons. So 8 minus 8, 0, which means that there are no electrons left over. So therefore, this is the structure of CH4. Okay, there's nothing else to do. CCl4. Now CH4, CCl4 are kind of similar, okay, because you have the 4 atoms here also with carbon and 4 atoms were here also with carbon. If they were just hydrogen here, now you have chlorine. So again, start with the compact structure, okay. Chlorine is more electronegative than carbon, so carbon goes in the middle. Now the total number of valence electrons are a lot more. Why? Because chlorine has 7 electrons and carbon has 4. So 7 times 4, that's 28, plus 4, that's 32. Okay, so that's the total number of valence electrons. And then you go ahead and subtract what you have formed the bonds of. So you form 4 bonds, 1, 2, 3, 4. So you take the total number of electrons, 32, and subtract 8 from it, and you have 24 electrons left over. Now, where do you place those 24 electrons? If you look at carbon, carbon is already happy. Okay, it's got 8 electrons and it does not need any more electrons. So which means that you can take those 4 electrons and you can distribute them all over the chlorine. So 24 divided by 4 is 6, and so you give 6 electrons each to chlorine. Okay, this is how it works. So similarly, go on for these two yourself, and I'll cover C and minus, which is a cyanide ion, because this is a negative ion. So here we have only 2 atoms, so C and N joined together 1. Now, where is this 10 coming from? Total number of valence electrons. Carbon has 4 and nitrogen has 5. So that's 4 plus 5, 9. But we have 1 negative charge, so therefore you have to add that on here, so which gives you 10. Okay, so 4 plus 5 plus 1, that gives you a total of 10 electrons. How many are involved in bond? 2 right now. So 10 minus 2 is 8 electrons. So which means that we have 8 electrons left over to account for. So then we go ahead and distribute the electrons as well as we can. Carbon can have only 4 electrons, okay? Maximum it can have 8 electrons when it's fully bonded. So this is what the structure would look like if you distribute 2 electrons on carbon and then 6 on nitrogen. So nitrogen is pretty happy right now, but carbon is not happy. Nitrogen is okay because it's got the 8 electrons, 6 from here and 2 from the bond. So it's sharing 8 electrons and it's fine. But carbon is not happy because it's got only 4 electrons, and technically speaking it should have 8 electrons. That's the whole reason for it to bond. So it's not very happy. So what we have to do then to make it happy is make sure that we share more electrons between carbon and nitrogen. Okay, so carbon can have up to 3 or 4 bonds. So here we form 3 bonds more, 2 more bonds between carbon and nitrogen. So now carbon is happy because it's got 2 electrons over here and it's got 1, 2, 3, so 6 electrons over here. So now we have 8 electrons. Okay, 1, 2, 3, 4. and fourth one is over here. So 3 pairs here, 1 pair here. Nitrogen is pretty happy also. Okay, so you can see that this structure where carbon and nitrogen are sharing more electrons is a lot more stable structure than what we had before with just one pair of electron being shared. So now you go ahead and put square brackets all around and put the negative outside, because that extra electron is really helping out over here. Okay, and because this is a polyatomic ion, you have to draw the square brackets. Okay, in case of oxygen over here or water here, all the other ones you did not have to draw the square bracket, but because you have an extra electron, where do you put that? Do you put that on carbon? Do you put that on nitrogen? You don't know that yet. Okay, and so therefore you go ahead and put the square bracket and put the negative outside. Now there are some exceptions to the octet rule. We learn about the octet rule 888, or we say for hydrogen do it, and we keep saying that this is how it should be, okay, all the time, but there are exceptions. Okay, and I was telling you before also that sulfur, for example, can have 2 bonds and it can have more also. All right, so there are exceptions to the octet rule, and there are 3 exceptions, okay, that we say. So we can have molecules which have an incomplete octet. Incomplete meaning less than 8 electrons. We can have molecules with an expanded octet, expanded meaning more than 8 electrons in them. And then we can have molecules which have odd number of electrons. So far, all the molecules you have dealt with, whether they have been ions or molecules, they've all had paired electrons. Whether they were bonded or non-bonded, they were all pairs of electrons. So an exception would be if there's an odd number of electrons. So these are the 3 categories for exceptions to the octet. Let's look at the first exception, okay, which is for incomplete octet. And the example that we're going to take here is for boron trifluoride. Boron has 3 electrons, it's in group number 3, and fluorine has 7 electrons, and we have 3 of those. So we have a total of 24 valence electrons. So we write out the structure, and this is what it comes out to be, with boron in the middle, which is the lower electronegative element, and then fluorine on all sides. And fluorine gets all the electrons, okay, because boron can have only 3 electrons and all 3 of them are bonded. It doesn't have any more, so which means that even after bonding, it does not really have 8 electrons. It has only 6 electrons. If you want to try and compensate for that, okay, and say, okay, I'm going to try a different structure for this one, then it turns out that you can draw a double bond between boron and fluorine, okay, but if you do that, then you end up getting formal charges, okay, -1 for boron and +1 for fluorine. And we just learned, okay, about formal charges that, you know, it's much more stable for structures to be neutral, okay, rather than have formal charges, which means that the left one where the boron has no octet is still more stable than the one with the formal charge, okay, because this is the compound that exists, all right, without the formal charge. Well, it's all right, it's fine. This is how these compounds exist, all right, and so it is possible. The kind of compounds that you find with incomplete octet are going to be beryllium, which is in group number 2, boron, and aluminum. Okay, some of these compounds are going to be with incomplete octet. So you can just look at the periodic table and mark these compounds, okay, or mark these elements. They cannot have a full octet. Okay, so the only way they can have a full octet is if they are ions, okay, which means extra electrons are given to them. So what generally happens is that when they exist by themselves, they will kind of dimerize, okay, which means that they will start sharing electrons from each other, and this is how they will exist, all right. This is not such an important thing for you to focus on right now. The most important thing is for you to focus on that you can have incomplete octet, okay, but the fact is that these compounds do exist is because of this kind of a stabilization, okay, that can occur. Now let's go on to expanded octet. In case of expanded octet, you have more than 8 electrons, okay, in there. This usually happens for the 3rd period, okay, in the periodic table. So the 3rd period starting from sodium. So we have sodium, magnesium, aluminum, silicon, and then phosphorus is where the covalent bonding starts. So phosphorus, sulfur, chlorine. Any of these elements and then all the elements below it, okay, they can all have more than 8 electrons. And the reason for this is because they have d orbitals in them. Starting from shell number 3, you can have d orbitals. Before shell number 3, which means in shell number 1, you only have s electrons, only 2. In shell number 2, you can have only 8 electrons. S and then P. Okay, so 2 plus 6, only 8 electrons. But by the time you come to the third one, you can also have the D electrons. It's just that you don't fill them until after you fill the 4s2. So which means that these orbitals are still available for taking electrons. All right, and so that's what's actually used in case of the expanded shell. So for example, we can have sulfur. Sulfur is just below oxygen, okay, in the group, in group 6. So which means it has 6 electrons, okay, 6 valence electrons. So 1, 2, 3, 4, 5, 6 valence electrons. And as you can see in this structure with SF6 is that it is bonding all of its 6 valence electrons with 6 fluorines. Okay, so which means that now after bonding with 6 fluorines, sulfur has 12 electrons, 1, 2, 3, 4, 5, 6, the 6 bonds times 2. So that means it has 12 valence electrons, which is 4 more than what it should have, okay, because it should technically have 8. Now, it does not mean that sulfur will only have expanded shell, okay? It can still have the normal octet. But the thing is that looking at the compound that it's forming, you have to decide whether it's going to be the normal octet or the expanded shell. So you can have both, all right? So be careful when you're writing the Lewis structure. Xenon fluoride. Now this is interesting because xenon is actually a noble gas, okay? And so I have this over here because technically speaking, xenon is not supposed to form any bonds because xenon is a noble gas. But again, because of those d electrons, okay, it can form bonds. So it's the electrons that are coming in are not going into the s or the p. In case of sulfur, they're going in s and p also. But in case of xenon, the s and the p are completely filled up. So which means any extra electrons that it gets, okay, which is these 2 electrons that it is getting, these 2 electrons are going to go into the d orbital then, okay? And so now xenon has 22 valence electrons and xenon difluoride has 22 valence electrons and xenon has 10 valence electrons, okay? And so 2 more than what is usually required. So again, remember group number 5, 6, 7, all right? And then from phosphorus, sulfur, and chlorine, and anything below that, okay, that is a non-metal. So for example, bromine, iodine, selenium, these, all of them, they can all have expanded shells. So you just have to look at the compound and determine if you are going to draw the expanded shell. The last exception for the octet rule is the odd number of electrons. The major culprit here is nitrogen. Nitrogen has 5 valence electrons, which means one of the electron is unpaired to begin with. And because of that unpairing of electron, it causes some sorts of problems in all of these structures, but they're all stable structures. Okay, it's just that they have an unpaired electron in them. Okay, so for example, let's look at NO, which is nitrogen monoxide. And when you write the structure for nitrogen monoxide, this is what it should be, which is nitrogen and oxygen, where they're both bonded by a double bond. So if you look at the structure on the left and the right, the only difference between the two is where the single electron is. Okay, so here on the left hand side, oxygen has 1, 2, 3, 4, 8 electrons. Nitrogen has 1, 2, 3, 6 plus 1, 7 electrons over here. Here nitrogen has 1, 2, 3, 4, 8 electrons. Oxygen has 1, 2, 3, 7 electrons. Okay, so is one structure better than the other? And the only way to figure out which structure is better than the other, even though they're in resonance, it doesn't mean that both structures are equally stable. Okay, it just means that you have movement of electrons, but you can have more stable structures than others, okay, in resonance also. So, but in this case, are both structures equally good? Well, the only way you can figure it out is by doing the formal charges, okay? And so the formal charges for nitrogen monoxide for the first one is 0 and 0 for nitrogen and oxygen, whereas in the second case it is +1 and -1. And So the zero formal charge structure is much better than the one with the formal charge. Okay, so which means that the single electron is much better on nitrogen than it is for oxygen. Okay, and that's of course makes sense because nitrogen had the single electron to begin with. Let's take another example, NO2, nitrogen dioxide. Okay, in case of nitrogen dioxide, we have 17 valence electrons, again, odd number of electrons. And when you have odd number of electrons adding up, then we have issues. Okay, and so here are our issues, that we have so many structures that are possible. Okay, so we keep nitrogen in the middle because it is less electronegative. Oxygen is more electronegative, so it goes out. And then you can see what the differences in all of these structures are. Okay, and the differences, of course, is the movement of electrons. In the first case, the single electron is on the oxygen on the right-hand side. And then in the second case, the single electron is on the left-hand side. Again, just resonance structures. You still have the same total number of electrons. It's just that the electrons are moving around. So how do you know, again, which structure is the correct one? How do you find that out? Again, formal charge. Okay, that will give you the answer. And here are the formal charges for all of these different structures. So the one that has a 0,0 formal charge is going to be more stable. Now, I don't want you to take my word at it. Okay, I am not trying to talk too much here in these presentations, but the best thing for you to do is to actually calculate all of these different formal charges. I've already shown you how to do that. So calculate the formal charge and you will see that you come out with 0,0 here, and then here are some charges on the right hand structures, which means that the left two structures are the predominant ones. Okay, so these are the three exceptions that we just learned about octet. Your key takeaways from this PowerPoint should be able to draw the Lewis dot symbols for elements, for example, sodium with just one dot and chlorine with 7 and such. Then understand the concept of ionic and covalent bonding and what is the difference between the two. The octet rule, which is of course making sure that you have the 8 electrons in the valence shell. There's also the duet rule, which was very tiny, only for hydrogen, okay, but that's still there too. And then, of course, Lewis structures. Lewis structure is how you would show the ionic and covalent bonding that's going on. And they, of course, it's different for both of them. So Lewis structures, Lewis structure, make sure that you learn how to draw this. This is very important because, again, this is the foundation for going on into the next chapter. So if your Lewis structures are not correct, then everything else is going to be wrong as well. So please make sure you practice enough. And then we talked about, of course, the exceptions to the octet rule, where there are 3 exceptions. So please know these also, and not just know that these are the exceptions, also try to understand why this is the exception. Okay.